And so we have been talking about verification, right? And we have looked at Verilog. Okay, we have looked at we have started looking at system Verilog. So system Verilog is a hardware verification language more than anything else, and its main purpose is to um, perform verification. Okay. Whereas Verilog has been used in this synthesis as well. So you can write Verilog code which can be synthesized, but system Verilog is not meant for that, right? So, all right. So we have gone through many of the data structures, right? So you may have realized by now that system Verilog is a lot like, it has a very close resemblance to C and C++, right? So to be a good verification engineer, you should have a little bit more of a software leaning. Okay? Should learn how to use the constructs effectively, and so coding is something that you must be inherently good at. Okay, so I hope that point is clear. Somebody was asking a question. I don't know. So I forgot to see what the question is. Let me see if I can open the chat box and see. What does it mean? How LUR works means? What does it mean? Yeah, in what exactly are you asking? How what works? If you can rephrase your question. Oh, okay, okay, okay. I got it. I got it. Right, right, right. See, that was more of an assignment, but I can still explain. LRU, not LUR. Okay, that is why I was not able to understand. LRU means least recently used. Yeah. So we were talking about cache, I think, right? That was the exercise I had given. It is not a mandatory exercise. It is something for you to think about. Yeah. Dr. Poonam Kadam, sir, does that mean that designs are very long and very very? Yes, yes, you are right. Remember that design and test benches are separately developed. Okay? So as a result, those who develop RTL will do so in Verilog, and those who develop test benches will do so in system Verilog. Yeah. I think so the question was on how to use how to use that least recently used or something like that. So this is our memory. Yeah, I think I labeled them as 0 to 63. So 63 blocks or pages. Some people use the word blocks and some people use the word page. And each block, I think we said had 1K. So they could be 1 kilobytes. So total memory is 64K. So how many bits are required to address the memory? If we have 16 bits, I'm sorry, if we have 64 kilobits or kilobytes, how many bits are required? We need 16 bits. Okay. Because you will need to address any one of the 64 kilobyte, right? So there are 0 to 65,535 bytes. And the CPU will produce an address which is 16 bit. Out of that, see, 10 bits will indicate the byte address, and 6 bits will indicate the page address, right, or the block address. So this particular block has the address 0000. This guy has the address 1111. And within that, the block addresses will go from 10 zeros to 10 ones. Is that clear to everybody? Okay. Now we don't have, we cannot build, assume that we cannot build 64 kilobytes using high speed memory. So we'll keep a cache which has 8, there is only space for 8 cache blocks. Each of these is 1K. Each block is 1K. So totally 8K is a cache. So we can further divide this into two parts, 3 bits and 3 bits. So what we are saying is when we map the cache block to the memory block, right? So one cache block can map to about 8 memory blocks. Okay. We have assumed fully associative caches. That means any one of these memory blocks can reside anywhere. Okay. See, for example, if we call this this is cache block 0, this is cache block 1, this is cache block 7, right? And here any one of these could be present. Memory block 0 could be present, 1 could be present, 2 could be present, 63 could be present. The same is true for all the others. There are other ways to map. You could say I'm going to use direct mapping. You could say set associative mapping. Like that, there are other methods. So we are keeping it simple. We are saying that any memory block can be loaded anywhere. wherever there is space. So at some point, I think in the example I gave, I had assumed that, see, when the program begins to work, we don't know where the program is, right? So imagine that there is a program loaded here. So maybe this corresponds to block number 4 and 5. So the program may assume that nothing is loaded in the beginning. Then it will, when the program generates an address for block 4, we will want block 4 to be loaded. Then block 5 may be loaded. And this particular program may complete everything in block 4 and 5. So then there is no problem at all. But occasionally, let us say it asks for 6 and then maybe another 17 and things like that. So every time I find that the block is not in the cache, that is a miss. So we talk about hits and misses. So hit means whatever I was looking for, that particular memory is already loaded in the cache. Whereas miss means that particular memory block is not present in the cache. And when that happens, we have to load the entire block. So in this example, initially 4 was loaded like that because it was a miss. Now, how do I know whether it's a miss or what? So what they do is with the help of, there is a memory called tag memory. So when let us say here, there are 8 of these. Okay, let us say there are 8 of these. Each will be 6 bits. So this particular entry may show 4 because I have loaded block number 4. The entry here may be 5 because I have loaded 5 here. So this is how we keep the, if the memory comes from the CPU and we look at it as a 16-bit address, this part tells me which memory block it is. And let us say this happens to be 001010. That means we are looking for block 10. So we have to search for that pattern here. If that pattern is not there, then we get a miss. Okay. So we search through the entries in the tag or the tag memory. And when the miss is there, we have to bring that block. Okay. Now to bring that block, we have to have a block which is available. That means it is not currently storing anything useful, or it's a very old page or an old block which is unlikely to be used. So what we do is every time So let us pretend that let us pretend that 4 was present here, 5 was present here. Then let us say we have 6 here, 7 here, 8 here, 9 here, 23 here, and 61 here. We have to look at the order in which they were addressed. So maybe initially we got 4, then we had an access for 5, then 8, then 9, then 23, then 23 again, then 61, 7, 7, 5, 4. And then finally we got an access for, let us say, 18. Okay. So 4, 5, 8, 9, 23, 7, 61, they're already loaded. So we already have 1, 2, 3, 4, 5, 6, 7, and 8. I'm missing something. 4, 5, 6, 6. I think I may be missing. So there is already, all the 8 blocks are occupying. So when 18 comes along, or a request for 18 comes along, we have to see which one should be replaced. So because 4 was addressed most recently, we should not replace that because it is likely that it will be referred. 5 should not be replaced because we have just 7 should not be replaced. So like that, we'll identify the most recently used are to be replaced. I'm sorry, the most recently used ones should not be replaced, whereas the least recently used should be replaced. Okay. So in this example, 4, 5, 7, 61, right, 23, it is 5. Then 23 is again there, then 9, then 6, right, 8. So 5 seems to have not been used at all. Okay, it is the least recently used amount. So we knock off 5 and in its place we bring 8. So it's a simple algorithm, nothing complicated about it. This is called as least recently used. There are others like first in, first out. Okay. So you can use any one of these. So you need a hardware to check whether the block is present or not. So here is my tag memory. And I have 6 bits in each of the entries. And I have totally 8 entries. And when I get the address, I have to take the 6 bits, the most significant 6 bits, and so this will represent the byte address. And this is the tag. We have to search, and this search has to be fast. See, we cannot do one by one. So it may be necessary to put several comparators. Okay. So let us say in this example there are 8 comparators of 16 of 6 bits each, and they will simultaneously do all the comparisons, and either they'll tell you that there is a hit or they'll tell you that there's a miss. If it's a hit, all we have to do is go to that memory, cache memory, wherever it is loaded. See, we have to also figure out where it is loaded. Okay. We don't know which particular place it is. Like this may be the place where block number 23 that is being requested is loaded. So we have to figure out where this cache block is. And we have to access that block using this byte address. So if it's hit, we also can go and give the actual value. If it's a miss, then we have to inform. I mean, we have to basically go and load the data and transfer 1K bytes to the, we have to decide which one to be replaced, block to be replaced. And in that block, we have to copy 1K block bytes must be transferred. Right? And we can also remember that this is a new cache block that we brought in, so its age is 0. And all the ones that are already there, we can increment their age, saying that all of them have aged by 1. And we can look at the most aged block as the one which is ready for replacement. And like I may have mentioned to you, we also have to see whether the cache has been updated. So when I try to, I can get either a read request or a write request. So if I'm trying to read from the main memory, then after loading it after loading it to cache, we can access the particular memory being requested for and supply it to the CPU. But if the CPU is trying to write something to the memory, then should we write it in the cache or in the main memory, right? So if you only update the cache, then that is called write back. If you update the memory along with the cache, it's called write. So this one is in a way safe because we have gone ahead and updated the memory. It's a little slow. But if you are using write back, then you have to mark that particular page and say that this has become updated. Okay, there is a 1 bit that we can store with saying this bit has to be returned back. When that cache block gets replaced, at some stage we may have to replace that cache block by another one. At that time we can write the memory. So the block to be replaced, we can also inform whether it has to be returned or not. So this is how usually the cache controller is organized. Okay. Any questions? Did you guys understand? By the way, it is cache memory. Okay, it's not. It's spelled cache like this. It's not cache. So the word cache means a hidden hiding place. Go on. Let's move on to maybe some more concepts in Verilog. I'm sorry, system Verilog. So we'll go through the class idea. Okay, there is a concept of a class in system Verilog. See the struct, etc. Right? We already know. Right? If I wanted to declare a struct called complex, which has a real part and an imaginary part. So this declares a variable called C1, which is a structure. And I can write tasks, etc. to handle this structure. Okay. So I could write a task called display, which takes as input a struct complex. And here we can write dollar display percentage f plus j percentage f c dot real part c dot imaginary part. So in other words, what I have done is I declared the data type or the data structure here, and I separately went ahead and wrote a display. Like this, I can write other tasks and functions. Okay, there could be another function which gets me the absolute value. So this will return the square root of real part square plus imaginary part square. So we can say return square root of real part square plus imaginary part square. So this has to be, let us say, a module called test. So I could write C1 dot real part equals 3, C1 dot imaginary part equals 4, then display C1, then display value equals this absolute value.
So the variable is C and C1. Line number 4, it is C1.
Yeah, the variable number is same. Yeah. That's a valid syntax. Sorry. Mhm. Value is not correct, no? C dot real part square. It should say here. The return value of the function is real. So now it's okay. So I'm not sure why it was not accepting that complex here. That is valid. I don't know. So we have declared a type called complex, which is a structure. Okay. And inside it has a real part and an imaginary part. Then we have declared a task and a function. The task simply displays the complex value. It takes an input called complex. I'm sorry, it takes an input called C, which is a complex number, and accesses the parts by using C dot real part and C dot imaginary part. Then every function should have a return value. The type of the return value should be specified. And here we are simply doing square root of the real and imaginary square. Right? So this is already available. Okay, this is already available. But the problem with this method is, see, when you want to work in a team, right, and you want to share, code, this is not very amenable, right? So struct is, present, and then display is separate, absolute value is separate, right? And like this, tomorrow somebody may come and display, they may declare another type of something here, and they may declare, so everything gets separated. They're all not together in one place. The complex number is a data structure, and these are only meant for complex. Okay, it's better to have them all in one physical unit, and that is what the class achieves. Okay, we can create a class. So let me share this with you guys. So this is complex number using struct. One can also declare a complex class. So we can say class complex. And here we can declare uh, real real part. Imagine. So far it is seems to be very similar to the struct. Okay, we just declared some data, but we can also declare a function called new, which takes as input maybe R part and I part, which are both reals. And this one, we can say real part equal to R part and imaginary part equals I part. So I have created a what is called as a construct. So this new is a special function. It creates an object of this type. So here I could write a module where I could say complex field. It looks a lot like the type def, okay, except that it is a complex number, right? And later I can go and say C1 equals new, and I can say 3.04. So this is how I will use it. And I can build the same task here, except that it is not, I'm not going to say what to display. I mean, that is this complex number. Okay. So I'll say dollar display percentage of plus J percentage of, and I'll simply refer to real part and imaginary part. So it knows where they are, and I don't have to pass any argument. So now I can say C1 dot display. So actually display will take this object. So to try this, it should do exactly what we did here. So you can see that it displays 3 plus J4. And we may be able to create a function also. So this returns this real part square plus imaginary part square. So you can see the difference between the two. Statement. See, what it is doing is if you don't specify the return value or the return type, it returns it as an integer by default. So that goes wrong. So you have to always watch out. Is that clear? So now somebody in the team would develop this class entirely and store it in some file. And the others can reuse that as so this allows reuse in a much better way. The class concept allows reuse. So I can declare any number of complex values. I can say C1 comma C2. So it is so easier to just generate more complex numbers. So here I can say C2 equals new 6.08.0, right? Now suppose I want to add these two values and create a new complex number, right? So I will say something like function, let us say add. See, this function will be called like this. So this means add C1 and C2 and maybe return in C3. So we want to create C3. So we should be able to add C1 and C2 and return C3. So notice that in this add, all we have to do is complex C2. C1 is already, it is there already. So we are going to use C1 dot add. So the first argument is C1. We don't have to pass it. And what does it return? It returns a complex number. Okay. So add returns a complex number. So add will add C1 and C2 and returns a complex number. So here I could define a complex number called result, and I could assign result equal to new. Here I could say C1 dot real part plus C2 dot imaginary part. I'm sorry, C2 dot real part. And then C1 dot imaginary part plus C2 dot imaginary part. Then return that. Okay. So then return result. And then we can display C3 dot display. This is just real part, right? It is not C1 dot. Okay. It only refers to this real part. Okay. So that was a mistake. C2 is what is being passed on. So that should be used. Then for my own real part and imaginary part, I just have to refer directly to it. Is it okay? So there is a C1, this is C2, values of C1 and C2. and the value of C3 and so does it make sense to everybody? What is a complex number? I mean, what is a class? So tell me, you try writing a multiplication. Okay. So suppose we have to multiply two complex numbers. So I will take the other complex number and I will return a new complex number. So what is the result? The result dot real part will be what? See, if you have a plus jb multiplied by c plus jd, ab, I'm sorry, ac minus bd is the real part, and ad plus bc is the imaginary part. Okay. So here we'll have to say something like a is nothing but real part, c is c2 dot real part. It allows you to say this dot real part. If you want to make it clear what this is referring to, you can say this means this object has a real part minus CD. Okay, so CD is this dot imaginary part multiplied by, I'm sorry, mm, what is it? C is C2 dot imaginary part multiplied by this dot BD, right? BD is what? BD is this dot imaginary. Multiply D. D is C2 dot imaginary. Similarly, result dot imaginary part is AD plus BC. AD happens to be this dot real part, C2 dot imaginary part, this dot imaginary part, and C2 dot real part. Then I can return. So here I can multiply also. So I can say C3 or C4 equals C1 dot non C2. We have to do new here. Huh? See, I am directly assigning. So before doing that, I should do result equal to new. We can say 0, 0. We can put zeros in the beginning. Yes, Rajendra Vyas, anything you wanted to ask? So remember C4, see in the previous one, here also I should do that man. This is not correct. We should say result equal to new. See, it didn't give me an error, but it's dangerous. We should. So this is where we allocate storage. By chance, it didn't give me an error. Okay. So if you just say result and try to assign, you don't have any storage, so it's wrong. Okay. I think I should have displayed the value, right? So this is the multiplication of the two. I hope it is correct. So 3 plus J4 multiplied by 6 plus J8. So 18 minus 32 and 24 plus 24. So I accidentally left out that new. So whenever you have a class defined, and when you say something like this, complex C1, C2, C3, C4, C1 are all pointers to that object. C1 points to the object, C2 points to the object, etc. Storage has not yet been allocated. Okay. So here is where that object gets its storage. When you say new. Earlier, when we forgot new here, it is just by chance that it went through. Okay. But if you have a bigger program where you have forgotten the new, it is definitely going to cause some problems. So we have to first allocate storage and then we can do whatever. So any questions about complex, I'm sorry, classes? Any questions? So you'll find a good treatment of classes here. So it introduces system Verilog introduces an object-oriented class abstraction. So if you start using things like classes, you are basically using object orientation. So here are some examples. Class packet. This is the data associated with the packet. And then you have defined a function called new, function called clean, function called issue packet, etc. So a class defines a data type. An object is an instance of that class. An object is used by first declaring a variable of that class type. It just holds a pointer or a handle and then creating an object of that class using the new function. So here is an example. Packet P equal to new. This variable P is set to hold an object handle to an object of the class packet. Constructor is important. You should understand how to form a constructor. And then I think I mentioned this. Okay, this keyword is used to unambiguously refer to class properties or methods of the current instance. So when I say method, these are all methods. See, this bar is a method. If foo is a method. You can also create a hierarchy of classes. Okay. Sometimes that may be useful. Maybe as a if you have complex numbers, right? Maybe imaginary numbers can be a subclass of that complex number. Okay. An imaginary number is nothing but the real part of that will be zero. So there may be some value in deriving a subclass of complex called imaginary numbers. Similarly, real numbers, I'm sorry, real numbers could be a subclass of complex. They will have the imaginary part to be zero. So you are welcome to create such subclasses, etc. But this we may or may not use so many of these subclasses, etc. Sometimes it is useful. So first, let us make sure that we all understand how to use a class. I think the class construct is accepted even in system Verilog. I'm sorry, ICARS Verilog. So you should be able to do this, to my knowledge. Yeah, see, this works. So you should be able to do an exercise on complex on your own. So try creating a new class called set. So what is the difference between a set and a queue? In a queue, you can add, see, this is a set. This is a queue. And there you can have 4 again, and 3 again, and 2 here again. But in a set, you only have each element only once. Okay? So if you try to add 2 again, nothing will be done. So that is the difference between a queue and a set. So sometimes this may be useful. Similarly, we may want to, for the set object, we may want to define a union. We may want to define intersection, difference. So these are some of the methods that we can implement on. So I want everybody to grab a piece of paper and think about how you will create a object concept or rather class concept. It was already there. Sorry, this is already there. So I'll give you a few minutes to think. Then you tell me, how you plan to go about creating such a set. If you want to look at this code, you can. So any thoughts?
Using dynamic array,
Yeah, you can use dynamic arrays. It's a good idea. You can use dynamic arrays. Why did you choose dynamic array? Any reason?
that helps us to add on to the
Yeah.
set values.
Yeah. You can use dynamic arrays. You can use queues. Good. So help me. Class set. So we have to decide what we are going to put inside. Is it a set of integers or strings or what is it that we want? Okay. We can put integers of, maybe test vectors of some kind. So we could define type def. So let us say we take 7 to 0 or 5 to 0 as a tag. So a tag is a 5 bits. A tag is a collection of 5 bits. Then we could say tag. We could call it as tag array or something. So if you do it like this, it is a dynamic array. Tag array is an array of tags. Right now it's empty. We could create a function. I'm sorry, yeah, function new, which is a constructor. So when we create the set, maybe we'll give some, we'll just take an empty thing, we just create a set. Because I don't know whether to create a set with one or two or three. We'll just say function new. If you want to give at least one value, you can say tag. So create a set with a single value. Then I could say something like tag, I'm sorry, tag array equals new one. We want to have one entry. No, I think it is new like this. So that is your set.
Yesterday we discussed about some appending function. Can we use that?
Yeah, you should use. Don't hesitate. You should boldly go ahead and try. Okay. After all, you have nothing to lose. We can have a thing called display. So this will display the set. Okay. So dollar display. See, write will display this without putting a new line. Then we could write integer I. Then for I equals 0, I less than tag array dot size I plus plus. Okay. Dollar display. I'm sorry, dollar write percentage. Let us say D comma tag array of I. So this helps me, and then finally we'll write dollar display. So this could be a way to display the set. It puts these flower brackets in the beginning and end, and then it goes through each of the. So if we create a module called test set, you can declare a set called S1, right? You can start by saying S1 equals new, let us say 5. That is my value I want to give. Okay? Then S1 dot display. So that hopefully will display the flower bracket 5 flower bracket. Maybe 11%. Can you look up and tell me what is? Can somebody look up the PDF and no, this may not matter. This may not matter.
Sorry, line number 6, what is that index 1 represent?
I'm giving space for one.
Okay.
I want to just allocate storage for one set because the user will create one like here. There's something wrong. For I equal to 0, I less than tag array dot length I plus plus. Hmm. Let us try cadence. Price is also not correct. Huh? Size is actually correct. Now, why is it writing 0? Oh, I think we forgot to write that. See, when we created this set, after that we should say tag array of 0 should be equal to t. See, this we forgot. So it is writing 5. Okay. So we created a trivial function called new. I don't know whether it will allow new 0. Ideally, I should create an empty set because when somebody creates a set, nobody wants to create with some value. But I don't know whether it will accept this. It may cause some problems. Oh, it works. So it will function new, it is not doing. So I like this. So create an empty set. What else can we do? We have created a function for creating an empty set. We have created a function to display the set. What else will make sense? Add something to the set, right? So maybe we can say task add. And what to add? So maybe we could say tag t. I don't know how whether it will accept. See, I don't know how many elements will be added, right? I can add one, that's not a problem. But sometimes it will be useful to give add multiple. And now what I have to do is tag array equals tag array new one. So this means add this storage and call this as tag. So here we can add s1 dot add. So this should display 5 in the next line. Sixteen.
So if we call multiple times this function add, then it will only replace. Will it append?
No, it will append. It will append. See, you read the documentation which I gave you yesterday. Okay. Array uh, No, dynamic array, right? Sorry, dynamic arrays. See here. See, address new 100 and then this. I think that is the error I have made. New 200 and then this. So I should replace those two. So here I should say new one, then say like this. So it has added 5. So we can add a few more elements. Unfortunately,
Sir,
we don't know how to
this
add
keyword,
multiple.
the
Huh?
new is already a keyword, isn't it, sir?
What?
The NUW, new is a keyword known to
Yes,
system. So
yes.
can we use again as a function name?
New is a function only I'm creating. I'm creating a function called new.
But already it is a keyword in system Verilog for
It is
dynamic
meant for
array.
this purpose only. Okay.
Okay.
Hey, there is something wrong in our code. It is not appending. So what should, you know what? I should say like this. See, I should add to this, right? See, this new one is wrong. The new one is what we should do is uh, tag array dot size plus. So this one, hey, what is this? Tag array. It clearly says preserving the new values. It didn't preserve your value, did it? I think this also, I should not add it at 0. I should add it at the end. So it should be fine. What do you say? Tag array dot size plus. Mm, yeah. What do you say?
Or is it a size -1?
Where? Here.
Array dot size -1 because it will start from 0 to n
Oh,
minus.
maybe you're right. You're right. That's right. That's good. Good catch. So indexing begins at 0. So for those who didn't follow, let me repeat it. So we created a class called set, and it was suggested that we use a dynamic array to maintain the elements of the set. Okay. So use a dynamic array to store the elements. And the constructor is very simple. Okay. We create a zero length dynamic array. That's all. Nothing else is done. Display just writing flower bracket and displaying all the elements one by one, and then end with the flower bracket. Add requires us to specify a whatever we want to add, and we add one element. So we have to make space for one extra element. We already know what the size is. So that we have to add one more. We are making space for one more. There may be a clever way to accept multiple. Okay. See, if I say like this, I can add 5 elements at a time. Okay. But see, I don't know whether I can make a variable here. Okay. So one is okay or any constant is okay, but I don't know whether it will allow me to add any number of them. There may be a way. Then the last address is the size -1. Then store the element there. So T is the element that we have received for storing. That is added here. So here we created a set called S1, and we displayed the empty set, and then we added a lot of things, and then we displayed. So now help me write maybe remove. So I want to remove a particular set. I don't know whether it's going to be very easy with dynamic arrays. It's very tricky. Any ideas on how to implement remove?
So this element T may be or may not be there in the set, isn't it?
That is a different matter. But if it is there, how do you remove
Okay.
it? The delete will delete the whole thing. Okay. But we can, that I don't think there is any other way. I can't think of any other way. We have to make a copy of the old one, and then that's the only way I can think of it. It's not very. So we'll say set S10. We'll create an empty set. And then we go through all the elements in the set. If tag array of I not equal to t, then stem dot add tag array. It's really inefficient. Then we have to delete our existing array, tag array dot delete. Then create tag array again. Then copy everything. We created a temporary set called stem. Then we went through our tag array, and if it does not match this t, then we add it to the temporary set. So the temporary set will have everything other than we have made one mistake. Huh? Add should not add if it's already there, right? But we have not checked. Right? So it's not really a set. So we should check. So if it's already there, then we don't do anything. So at the end, if element exists, don't do anything. If it is not, then do all this. And again, I don't know that there is a way to break the loop. I don't know that there is a break command because there is no need to continue further. If we find the element, we can just break out of it. I don't know where it's there.
We can have some lunch break between 1 hour or so.
Sure, sure. No, no, I meant this break as the this break in the statement.
Oh, sorry, sorry.
Maybe you have reminded everybody about break. Break seems to be there. So we can try by adding s1 dot add 6 again. Okay. If that works, then the add is working correctly. Yes, so it should be s1 dot tag array dot size. Line number 37. Same thing in 38. So Vinit, shall we give them a break at 2 o'clock or something for lunch?
So that will be good, sir. Or 1 hour, maybe so 45
So
minutes.
our add unfortunately is not working yet. 6 is repeated. Element exists is 0 if for I equal to 0, if tag array is equal to p, element exists is 1. If not element exists, so I think we should say not like this one. Not. See, I made a mistake. See, not is the correct way to check not. If you say tilde, element wise, it will sort of invert. Okay, so that won't work. Okay, so we should use not. So now we can try s1 dot remove. S1 dot display. So at least the set addition and remove are working. Similarly, we have to define s1 dot union and s1 dot intersection and maybe s1 dot difference. These are some useful things that we can add. So you do one thing, you take your break now, okay, and after the break we'll continue. Maybe many of you are hungry. Okay. Any questions before we break? All right, you take a break. Vineet, when should we come back?
Sir, maybe 1 hour, something.
Yeah, fine.
3 o'clock.
So around 1:55 something.
Yeah. So we can say 2:50 or 3 o'clock.
Yeah.
Sir.
What?
3 o'clock, sir.
Oh, I'm sorry, it is now 1:50, right? Sorry, 2:50 or 3 o'clock is fine. My mistake. 3 o'clock is good.
Yeah. Okay, fine.
Okay. Should I? You will stop recording and all, right? Otherwise, it's a waste.
गीता रिकॉर्डिंग रोक लीजिए